Let's start with today's featured paper, Jacobian Scopes, Token-Level Causal Attributions in LLMs, by Tony J.B. Liu and Christopher J. Earls. Here's a full breakdown. Contribution 1. Jacobian Scopes Framework, a novel suite of gradient-based, token-level causal attribution methods, named Jacobian Scopes, was introduced to interpret LLM predictions. These methods quantify how input tokens influence specific logits, the full predictive distribution, and model uncertainty, effective temperature. The core mechanism involves analyzing the Jacobian matrix, which captures the locally linearized relation between the predictive distribution and input embeddings, grounded in perturbation theory and information geometry. This framework addresses the challenge of understanding influential prior tokens in complex LLM architectures, providing a systematic approach to interpret emergent abilities and prediction mechanisms. Contribution 2. Multifaceted attribution variants. 3 distinct variants of Jacobian scopes were developed: semantic scopes, Fisher scopes, and temperature scopes, each targeting a different attribution objective. Semantic scopes attribute influence to the logit of a specific token, Fisher scopes to the full predictive distribution, and temperature scopes to the model's uncertainty, effective temperature. These specialized scopes offer a more granular and complete interpretation of LLM behavior compared to prior work, enabling analysis of not just what is predicted, but also the confidence and distribution of predictions. Contribution 3. Practical application and insights. The efficacy of Jacobian scopes was demonstrated through case studies revealing implicit political biases, uncovering word and phrase-level translation strategies, and shedding light on mechanisms underlying in-context time series forecasting. These methods were applied to diverse tasks, including instruction understanding, translation, and in-context learning, ICL, providing fine-grained, token-level causal attributions. This showcases the practical utility of Jacobian scopes in diagnosing LLM issues like biases and understanding complex emergent behaviors, contributing to more transparent and controllable LLM development. Contribution 4. Quantitative validation and accessibility. Attribution faithfulness was quantitatively evaluated on Lambda and IWSLT 2017 datasets across Llama 3.2, Qwen 2.5, and Gemma 3 LLMs, and the implementations were open-sourced with a cloud-hosted interactive demo. The quantitative evaluation provides empirical validation of the method's reliability and performance across diverse models and tasks. This ensures the reproducibility and accessibility of the proposed methods, enabling researchers and practitioners to apply Jacobian scopes to their own custom text and further advance LLM interpretability research. That was our featured paper. Today, ArXiv received 825 new computer science papers across 55 subfields. Let's look at the research landscape before we continue with the remaining papers. Here's an overview of today's 10 trending research areas: complex system control and optimization, user and data system analysis, reinforcement learning and adaptive control, advanced perception and anomaly detection, advanced optimization and policy learning, hardware design and formal verification, neural network properties and efficiency, advanced AI agents, and LLM orchestration. LLM reliability, bias, and safety, advanced mathematical and algorithmic techniques. Get this: Beethoven's Moonlight Sonata actually shares structural parallels with machine learning's latent space, a truly wild connection. We're also finally getting token-level causal attributions, helping us understand why LLMs say what they do. Now let's explore each of today's trends in detail, starting with number 1. Trend 1 of 10. Complex system control and optimization. Optimizing and controlling complex systems like power grids and aircraft using advanced analytical and computational techniques. This cluster covers 20 papers. Representative work includes modal analysis of spatial load correlation in AI data center-dominated power systems, spatial load correlation in AI data center-dominated power systems, and HPC-enabled generator importance assessment for RTO-scale resource adequacy planning. Trend 2 of 10. User and data system analysis. This cluster covers 130 papers. Representative work includes the frustrometer, detecting user frustration in data visualization tasks using biomarkers and interaction patterns, picturing perceptions, an open-source toolkit to uncover bias in humans and machines, and an agentic retrieval framework for autonomous context-aware data quality assessment. Trend 3 of 10. Reinforcement learning and adaptive control. This trend explores learning-based and adaptive methods for dynamic decision-making and control across diverse applications. This cluster covers 70 papers. Representative work includes a deep reinforcement learning (DRL) based transformer method for solving the open-shop scheduling problem, an integrated interpretable control effectiveness learning and nonlinear control allocation methodology for over-actuated aircrafts, and compressing image style training into a single model forward. Trend 4 of 10, advanced perception and anomaly detection. Developing sophisticated techniques and systems for enhanced sensing, interpretation, and identification of anomalies across diverse data modalities. This cluster covers 100 papers. Representative work includes morphology-aware sample assignment, overcoming IOU insensitivity for surface defect detection, occupancy-grounded room segmentation for hierarchical 3D scene graphs, and connections between pairs of filters improve the accuracy of convolutional neural networks. Trend 5 of 10, advanced optimization and policy learning. This trend explores sophisticated methods for optimizing complex systems and learning effective decision-making policies. This cluster covers 52 papers. Representative work includes which models perform better in inheritance reasoning, diffusion policy optimization without drifting apart, and price discovery admissibility in tokenized fixed income, identification, affine characterization, and the structure of the token-to-fiat mapping. Trend 6 of 10, hardware design and formal verification. This trend explores advanced methodologies for hardware design and formal verification, often incorporating AI-driven approaches and data synthesis. This cluster covers 87 papers. Representative work includes indirect computing model with indirect formal method, incentives of EdTech, a systematic review of EDU and LP research, and here SVA, a data synthesis pipeline, dataset, and benchmark for LLM-driven hierarchical hardware formal verification. Trend 7 of 10, neural network properties and efficiency. This trend explores neural network characteristics, performance, and optimization for robust and efficient operation across diverse applications. This cluster covers 85 papers. Representative work includes empirical evidence on genre time correlation in box office success using exploratory data analysis and machine learning, active inference for adaptive traffic signal control in noisy non-stationary IoT environments, and efficient on-device diffusion LLM inference with mobile NPU. Trend 8 of 10, advanced AI agents and LLM orchestration. This trend focuses on developing sophisticated AI agents and systems that leverage large language models for complex, coordinated tasks. This cluster covers 93 papers. Representative work includes UpInRPA, user portrait-based nested rollout policy adaptation for planning with large language models in goal-oriented dialogue systems. Position, AI must become planet-centered, not just human-centered, and Orchestra, 01, omnimodal agent orchestration. Trend 9 of 10, LLM reliability, bias, and safety. This trend explores how large language models perform reliably, fairly, and safely across various applications and evaluations. This cluster covers 121 papers. Representative work includes cross-dataset balloon question classification, supervised models, and prompted LLMs, the coin flip judge, reliability and bias in LLM as a judge evaluation, and benchmarking web agent safety under e-commerce deceptive interfaces. Trend 10 of 10, advanced mathematical and algorithmic techniques. Focuses on developing and applying advanced mathematical theories and sophisticated algorithmic techniques to solve complex problems. This cluster covers 67 papers. Representative work includes on the impossibility of parabolic factorization of certain Kasdan-Lustig basis elements. Non-simple T prescriptions yield T complexity gains infinitely often, and a WKB-related time-stepping scheme for differential equations describing oscillatory systems. That's the full research landscape for today. Remember, our number 1 paper, Jacobian Scopes, token-level causal attributions in LLMs, was already covered at the top. Now let's continue with papers 2 through 10, one by one. Up next, our second paper out of 10, Selective Agentic Recovery for UAV Autonomy with a Persistent Mission Runtime by Taewoo Park and Hwangnam Kim from Korea University. Let's break down its key contributions. Contribution 1, Persistent Mission Runtime, PMR. The Persistent Mission Runtime, PMR, is a novel UAV recovery framework designed to integrate external agentic reasoners for high-level recovery. PMR maintains the mission loop and safety-critical execution locally, only invoking an external agentic reasoner on demand, with all return decisions undergoing parsing, verification, safety filtering, and mapping to local executor actions. This architecture enables agentic AI to support UAV autonomy by providing recovery reasoning for blocked passages or no-progress behavior, while mitigating the latency, resource cost, and uncertainty associated with remote calls on physical UAVs. Contribution 2. Learn CVI for mission success. Learned cognitive value of invocation, Learn CVI, is a compact admission gate that dramatically increases mission success rates in challenging scenarios. It estimates the likelihood that remote agentic reasoning will improve near-term mission progress sufficiently to justify its operational cost, thereby selectively admitting remote reasoning. In a 400-run Gazebo/PX4 benchmark, Learn CVI boosted success from 5.0% to 95.0% in hard/ambiguous regimes, outperforming one-shot and periodic reasoning baselines by 20.0 and 32.5 percentage points, respectively. Up next, our third paper out of 10, Microswarm Locomotion Optimization in Dynamic Flow Using Multi-Objective Multi-Agent Reinforcement Learning by Joseph Berman and Orangao from the Hatter Department of Marine Technologies, Leon H. Charney School of Marine Sciences, University of Haifa, Israel. Let's break down its key contributions. Contribution 1. Hybrid CFDM Model Framework. A hybrid CFDM model framework was developed, coupling a high-fidelity incompressible Navier Stokes solver with decentralized proximal policy optimization to control 16 magnetically actuated microrobots. This system navigated a pulsatile arterial waveform within a 2 mm channel, achieving progress rewards of 6.5 to 7.0, energy efficiency of 0.63 to 0.65, and smoothness of 0.97 to 0.99. The framework integrates physically realistic fluid agent interactions directly into multi-objective reinforcement learning, allowing the swarm to jointly optimize upstream progression, energy efficiency, and motion smoothness. This approach outperformed brute force baselines by more than 8 reward units on the primary objective, providing a scalable framework for microswarm control in challenging time-dependent fluid environments relevant to biomedical navigation and microfluidic systems. Contribution 2. PC-Grad for Multi-Objective Learning. Conflicting objectives in the multi-objective learning process were successfully resolved using projected conflicting gradient, PC-Grad, surgery. This technique prevented the collapse of energy and smoothness rewards during training, demonstrating that gradient conflict resolution is essential for stable multi-objective learning. PC-Grad operates by modifying the gradients from different objectives to ensure they do not oppose each other, thereby enabling stable multi-objective optimization where all objectives can be improved simultaneously. The successful application of PC-Grad highlights its critical role for stable multi-objective learning in complex microswarm control, allowing for the simultaneous improvement of multiple performance metrics like energy efficiency and motion smoothness. Up next, our fourth paper out of 10, Diffusion Policy Optimization Without Drifting Apart by Haojia Jiang and Nika Hadalab. Let's break down its key contributions. Contribution 1. Double drift phenomenon identified. The double drift phenomenon was identified as the root cause of instability in existing diffusion policy gradient methods. This phenomenon occurs when optimizing a variational surrogate, causing the ELBO to separate from the true log likelihood, which then misaligns the proxy policy gradient with the true policy gradient of expected return. This discovery provides a systematic understanding of why proxy-based policy gradient updates in diffusion models are unreliable, explaining the failure of prior methods to achieve consistent policy improvement. Contribution 2. DPOD Framework Proposed. DPOD, a novel diffusion policy optimization framework, was proposed to address the instability of RL post-training for diffusion policies. DPOD maintains type-bound behavior throughout training by interleaving self-distillation with policy-improving gradient updates, preventing the ELBO from drifting from the true log likelihood. This framework offers a principled approach for reliable policy gradient updates that are native to diffusion and flow policies, overcoming the limitations of prior methods that struggled with log likelihood tractability. Up next, our fifth paper out of 10, VideoWeave. Unlocking Geometric Consistency in Video Generation via Joint Geometry Video Modeling by Xuanji Xiang and Shuilong Li. Let's break down its key contributions. Contribution 1. VideoWeave Latent Space Framework. VideoWeave, a latent space post-training framework, is introduced to enhance geometric consistency in video generation. It adapts implicit geometry model features into geometry latents, which are then jointly modeled with video latents within a shared denoising space, allowing geometry to guide the generative distribution. This method offers a flexible and non-rigid guidance mechanism, effectively mitigating reconstruction errors and computational overhead inherent in prior approaches that rely on explicit geometry reconstructions. Contribution 2. GeoVid 80K Paired Video Dataset. A new dataset, GeoVid 80K, comprising 80,000 videos, was constructed to support geometry-aware video generation. Each video in GeoVid 80K includes paired appearance and geometry representations, specifically curated to facilitate the training of models that integrate geometric information. This dataset provides crucial support for joint geometry video modeling, enabling the development of frameworks like VideoWeave that leverage implicit geometry features for improved 3D consistency. Up next, our 6th paper out of 10, when recommendation denoising meets popularity bias, understanding and mitigating their interaction by Guohang Zheng and Guanchuan Zhang. Let's break down its key contributions. Contribution 1. Denoising popularity bias interaction. The interaction between denoising recommendation methods and popularity bias was formalized, revealing that monotone loss-based reweighting can suppress clean but hardtail signals. This interaction is quantified through the effective head-tail signal ratio induced by denoising weights, with a conditional reallocation result showing that a right-shifted loss distribution of tail positives increases this ratio under small loss reweighting. This formalization highlights a critical limitation of prior small loss heuristic denoising, demonstrating how it inadvertently exacerbates popularity bias by disproportionately penalizing long-tail items and reducing effective supervision for them. Contribution 2. Popularity-aware denoising, PAD. Popularity-aware denoising, PAD, a lightweight plugin framework, was proposed to address the identified interaction between denoising and popularity bias. PAD modulates denoising strength based on item popularity, applying stronger denoising to highly exposed items while being more conservative on tail items to preserve clean but hard long-tail signals. This method offers a practical solution to improve accuracy and diversity by balancing noise reduction with the crucial need to maintain long-tail item representation, particularly beneficial for MF-style recommenders. Up next, our 7th paper out of 10, SAFformer. Improving Spiking Transformer via Active Predictive Filtering by Zichuan Xie and Jinxing Xiao. Let's break down its key contributions. Contribution 1. Active Predictive Filtering Paradigm. SAFformer introduces a novel spiking transformer architecture based on an active predictive filtering paradigm to enhance efficiency and focus. This paradigm is inspired by the brain's predictive coding mechanism, actively suppressing predictable signals and prioritizing salient visual features for processing. This approach fundamentally addresses the computational overhead and lack of focus in prior passive-reactive spiking transformers, enabling more efficient processing of visual data. Contribution 2. ImageNet, 1K SOTA accuracy. SAFformer achieved a new state-of-the-art top 1 accuracy of 80.44% on the challenging ImageNet, 1K dataset. This performance is attained with a highly efficient model, utilizing only 26.58 M parameters and consuming 5.88 mJ of energy. This result demonstrates an exceptional balance between accuracy and energy efficiency for spiking transformers, significantly advancing their practical applicability in low-power scenarios. Up next, our 8th paper out of 10. Can post-training turn LLMs into good medical coders? An empirical study of generative ICD coding by Ziqing Wang and K.I.'s Ding from Northwestern University. Let's break down its key contributions. Contribution 1. Comprehensive post-training evaluation. A controlled empirical study revealed that prompting-only evaluation significantly underestimates the potential of generative LLMs for ICD coding. The study systematically compared discriminative baselines with LLM coders across prompting, supervised fine-tuning, SFT, and reinforcement learning, RL, under a common protocol and metric set. This finding challenges prior reports of generative LLMs as weak medical coders, emphasizing the critical role of task-specific post-training for accurate ICD prediction. Contribution 2. SFT as core capability enabler. Supervised fine-tuning, SFT, provides the main capability jump for generative LLMs to perform ICD coding. SFT adapts the model using labeled note code demonstrations, teaching a parsable output schema and an empirical code prior. This establishes SFT as a crucial step for enabling generative LLMs to move beyond inference time limitations and achieve foundational coding accuracy. Up next, our 9th paper out of 10, Crypto x AI, AI x Crypto, a survey by Sarah Allen and Samuel Breckenridge from Flashbots. Let's break down its key contributions. Contribution 1. Systematizing Crypto x AI Landscape. A comprehensive systematization of existing work at the intersection of crypto and AI was performed. This involved categorizing and structuring diverse papers, products, online posts, and companies to clarify the field's scope. The systematization provides a structured overview, cutting through obscuring buzz to reveal what has genuinely been achieved. Contribution 2. Summarizing key takeaways. Key takeaways regarding the opportunities and challenges in Crypto x AI were summarized. These insights were distilled from the systematized body of work, identifying overarching themes and significant findings. The summary offers a condensed understanding of the field's current state, guiding future research and development. Up next, our 10th paper out of 10, Moonlight in Latent Space. Chirality and Structural Correspondence between Beethoven's Op. 27 No. 2 in Machine Learning Mechanisms by Chun-Ing Claude and Jihan Luo from Claude Code/Opus 4. Let's break down its key contributions. Contribution 1. Music ML Structural Isomorphism. The three movements of Beethoven's Op. 27 No. 2 are demonstrated to be structurally isomorphic to fundamental machine learning mechanisms. This was achieved via computational analysis of the score, employing metrics such as Shannon entropy, Jensen-Shannon divergence, and contextual pitch embeddings. This establishes a profound, non-analogical correspondence between complex musical composition and computational architectures, offering a new paradigm for understanding both domains. Contribution 2. Musical Memory Architectures. The three movements of the sonata implement distinct memory architectures: streaming, recurrent, and periodic positional encoding. This discovery was made through computational analysis of the score, utilizing metrics like temporal memory decay and self-similarity matrices. This provides a novel, mechanistic understanding of how musical movements manage and process information over time, analogous to memory systems in artificial intelligence. That's all for today's ArXiv Computer Science Daily. If you found this helpful, please like, leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.